We're now starting to look at optimal control theory, but before we do so, we're going to look at the calculus of variations, which was started by Bolza in his lectures on the calculus of variations. I have a third edition, which is from 1973, but the earlier editions were probably much earlier than that. And we see that when we look at lectures on the calculus of variations, from that we have what is called optimal control theory, noted by Pontryagin in 1962. And that led to the maximum principle, and the maximum principle basically means finding a function that maximizes a continuous functional form. At the same time, or somewhat earlier, Bellman, in his book 1957 on dynamic programming, came up with a solution that was much more, what we would say, relevant for economists in some ways at least, because it led to numerically computational approaches and basically discrete solutions for a control variable. But we'll look at both of these in more detail as we go along. We start with the fundamental calculus of variations problem, which is to maximize some function of y between points x0. So we start with a function I of y, and we have a function that we're integrating, which is a function of x, a function of y, but y itself is a function of x, and then we have the derivative of y with respect to x, which we denote with this prime here as dy dx. And we're integrating this function f from x0, some starting point, to x1, some ending point. Now in economics, we will generally use, instead of x0 and x1, we'll look at t0 and t1. So then time becomes a very important element here. And we also note that we have starting values. Y at x0 is equal to y0, and y at x1 equal to y1. So this is the starting value, and y of x1 equal to y1 is the terminal value. So we can describe this in a more palatable form, I guess. We find the function y as a function of x that passes through the points x0, y0, and x1, y1, and that has the property that it either maximizes or minimizes a definite integral in which it and its derivatives appear. So we could see that here in this little diagram, which I squeezed in. We have y on the vertical axis and x on the horizontal axis. We have a starting value x0 here and a terminal value x1. And what we want to do is we want to find a function that starts at this point where y0 is equal to some value, and y is a function of x0. So we could put in front of that y as a function of x0 is equal to y0. And we're interested in finding a function that follows some kind of a path to the terminal value at y is a function of x1, where y is equal to y1. And we want to find a function that is somehow optimal, that either minimizes or maximizes the integral. So in this case, the solid line represents that particular function that we're going to find. So this would be our optimal function. And we refer to this as a fixed endpoint problem. Then we have different kinds of problems. We have a free right-hand boundary problem where we're able to choose where we want to fall at x1, what the terminal condition is. So our value of y at that point is free. It's not determinate. And any of these paths may or may not be the optimal that either minimizes or maximizes that integral. Then we have the free terminal time problem. So now, I use the word time here, but it's really a free terminal x problem. That means we can choose x wherever we want, but we have to hit this value y1, given that we have a starting value, y, a function of x0 equals y0, and then it could take any of these paths along here. And again, the path we choose depends on what the integral is telling us how to maximize or minimize. Then we have the fixed terminal surface problem, where we have some terminal surface here that we have to hit. And again, we start at y as a function of x0, which is equal to y0, and we follow a path that hits that, or terminal surface, somewhere along it. And again, the path that we choose is the one that optimizes that integral. And finally, we have the initial and terminal surface problem, where we have a beginning surface here, denoted by that psi of x, and an end terminal surface denoted by sigma x, and we're interested again in finding the optimal path that goes from any point on this particular surface to this particular surface over here, with the idea again that we would optimize that integral. So in the calculus of variations, the solution y of x must be continuous. It is possible, however, for the derivative not to exist at some point. So the solution path need not always be smooth. So here we have two examples, one where we start at A and we want to end at B, and we get a point here where the derivative disappears. Another example is this one here, where it disappears at this point there. But notice that the derivative has to be such that it approaches from a positive side. So if we're coming at it from this angle, all right, so we're sliding down here and we hit that point. At that point, the two have to be equal. All right, so if we're coming at it from this side or from this side, from both sides it has to reach that central point here where the discontinuity occurs. So this fact that there's no jumps or anything like that in these functions is a necessary condition for the calculus of variations. So while corners are permissible in the calculus of variations, discontinuous jumps are not. With discontinuous jumps, we have to go to the optimal control problem as formulated by Pontryagin and his colleagues. So again, we want to maximize or minimize this function I of y, which is equal to the integral, or maximizing or minimizing the integral from some starting x value to an ending x value. You can maybe think of that as times, from some starting period t0 to some ending period t1 of this function, which is a function of x, y, and y prime, where y prime is the derivative of y with respect to x. And where we have these conditions, y0 has to be equal to that psi x, and y1 sigma of x. And that's shown in this diagram here, diagram above, and we show it again down here. So we're trying to find this red line, which of these red lines is the best. And there are a whole bunch of those, not just those two. So in order to solve this problem, we rely first on the Euler-Lagrange condition, which says that the partial of this function f, this function here, with respect to y, minus the derivative with respect to x of the partial of f with respect to the y prime. So with respect to dy dx, and that has to equal 0. We also have the two transversality conditions, and transversality conditions refer to these points here. All right, so this one says you need to start somewhere on this line, and you need to end on this one. Some of the other transversality conditions we had in the diagrams above, where we started here and we followed this path or that path, and likewise these kind of problems. So the fixed terminal surface problem, those kind of problems are what we have. Now, so far we haven't looked at constraints. So now what we want to do is introduce constraints. So we want to maximize, again, we want to determine the function that maximizes this integral, where f is a function of x, y, and y prime, And we have these initial condition that y of x0 is y0, and the terminal condition that y of x1 equals y1. And we want to add this constraint. So st refers to subject to the constraint that g x of y, g as a function of x, y, and y prime with respect to dx, the integral over x0 to x1 is equal to k. We form the Lagrangian, and what the Lagrangian does is it's a function of x, y, y prime, and this Lagrange multiplier lambda. And the Lagrangian is simply equal to the objective function, all right, without the integral. So it's just this component of that integral function minus lambda, the Lagrange multiplier, times the g of x, y, y prime. Now we'll later write this as k minus g, but the k tends to drop out. So in that case, we would have plus lambda times k minus g. Again, the Euler-Lagrange conditions, now we have two of them, is that the first derivative of L with respect to y minus the derivative with respect to x of the derivative of L with respect to y prime has to be equal to 0. And then we have these two forms which look identical to this one. These two here. The first one is we take the objective function, we take the derivative of f with respect to y, and we subtract derivative with respect to x of f of y prime minus lambda. This is the constraint, g of y minus derivative with respect to x of g of y prime, and that has to be set equal to 0 as well. Now, in order to understand this somewhat better, it helps to have a couple of examples. So we're going to go through two examples. So we're first going to find the extremal for minimizing the distance between two functions, x squared plus y squared equals 4, and that's that circle here. And the circle, you'll see, has a radius of 2. And this function here, y minus 5x plus 20, 5x plus 20. So we have this function here, and we want to find the shortest distance between a point on this circle to this point, to any point on this line, y equals minus 5x plus 20. So what do? We want to minimize that distance, and we'll show that that distance is equal to from x0 to x1, and all the square root of that times d of x. So what we're trying to find is, we're trying to find this line here, and in fact, I've already given the solution here, and we're going to show how you get that. And this point here is our starting value. So we're going in this direction. This is our starting value of x0. This is our ending value on the circle here. And it turns out that that number is going to be 1.96. Remember, this distance here is 2, so we're just inside that 2 right there. All right, so now note that first off, this distance ds squared is equal to dx squared plus dy squared. So we're looking at the distance, and this is the Euclidean distance. It's the square root of dx squared plus dy squared, square root of that all, and that's equal to 1 plus dy dx squared times d of x, simply by multiplying and dividing by d of x. All right, then the Euler-Lagrange condition is that the function f of y minus derivative with respect to x of fy prime is equal to 0. Fy equals 0, and how do I know that? Well, if I go back up here, basically take the derivative of this function with respect to y, and there's no y in here, so it's equal to 0, and then fy prime is equal to 1/2 of that distance here. So we get 1/2 2 times y prime, and that's divided by 1 plus y prime squared. So if we solve these together, we get minus the derivative with respect to dx of f y prime is equal to minus d dx of y prime over the square root of 1 plus y prime squared, which is equal then, or set to 0. And we integrate both sides of 1, and we get y prime over 1 plus y prime squared. All square root of that is equal to k0. And if we solve this, we get y prime squared is equal to k0 squared divided by 1 minus k0 squared. And then y prime is simply the square root of k0 squared over 1 minus k0 squared. And we set that equal to k1. So integrating again, so once again we integrate this to get y, and we get y equals to k1 x plus k2. We'll denote that with a number 2. The transversality conditions are given by f plus psi prime minus y prime, all times f of y prime. So the first derivative of f with respect to that y prime, evaluated at x0, and we set that to 0. And then we have the endpoint condition, and we set it equal to 0 as well, and we evaluate it at x1. So we're given that sigma x is equal to y is minus 5x plus 20, and we are given that psi of x is equal to y equals the square root of 4 minus x squared. So then the first derivative of sigma x is minus 5, and the derivative of I think that might be a phi instead of a psi prime of x is equal to minus x over 4 minus x squared, all under the square root sign. So from this result here, we get that 1 plus y prime squared, square root of that, plus minus 5 minus y prime over the square root of 1 plus y prime squared is equal to 0, and we evaluate that at x0. Doing so, we get 1 plus y prime squared minus 5y prime minus y prime squared. All right, and all we've done is we've simplified this particular function. That leads us to 1 minus 5y prime, since this cancels with this, and then we can solve that for k1. K1 then is 0.2. Then from 3 up here, from 3, we get that 1 plus y prime squared, the square root of all that, that's this term, plus minus x over square root of 4 minus x squared minus y prime, all multiplied by y prime over 1 plus y prime squared, all square rooted, and evaluated at x1 and set to 0. When we do that, we get the same thing. This cancels that, and we get 1 minus x1 y prime evaluated at x1, and that gives us x1 k1 divided by square root of 4 minus x squared, set that equal to 0, and we solve for x1, and that's 1.96 as I mentioned above. Now recall that y was equal to k1x plus k2 from this expression way up here, number 2, and we then get that minus 5x naught plus 20 is equal to 0.2x naught plus k2, and we get that 4 minus x1 squared, square root of all that is equal to 0.2x1 plus k2. We solved these two equations for x naught and k2, since x1 and k1 are known. So here's our x1, and our k1 is 0.2. So then, doing so, we find that k2 is equal to 0, and x naught is equal to 3.846, and therefore when we plug in K2, here we get a 0, and we plug in the K1 from previously, from way up here. K1 is 0.2, and we get the function y equals 0.2x. And that is exactly what we found here, where this line here is 0.2x, x naught was 3.84 something, and this number here was x was equal to 1.96, x1. Okay, second example is find the function y of x that maximizes this integral, 7xy minus the derivative of y with respect to x squared times dx, where x0 is 0, yx0 is 1, x1 is 1, and yx1 is 5. And the area under yx is constrained to be 10. So 10 square units if you like. We form the Lagrangian. Here's the Lagrangian. Remember, we include that Lagrange multiplier. F of x, y prime minus lambda g x of y, g of x, y, and y prime, where f x, y prime is equal to 7xy. So this is the f part minus y prime squared, and g x, y prime is equal to y of x. And the reason for this is that the constraint set is that this integral from x0 to x1 of y of x is equal to 10. So the Euler-Lagrange condition is, again, the same way we set it up. Here's the objective function, and this is now our constraint function multiplied by the Lagrange multiplier. We set that equal to 0. So then, taking this derivative of x, and remember this is x here, with respect to y, now we get 7x with respect to y plus 2 times y double prime. So we've got the derivative d squared y with respect to dx squared. So this is the derivative of, and that gives us this 2y prime double prime. And then we have minus lambda, g of y is equal to 1, simply because it's g of y is dy dy, and that's equal to 1. And then if you take the derivative of g of y, the derivative of 1 is 0. Lambda is equal then, when you solve this equation, lambda is equal to 7x plus 2 times y double prime. So we get 2y double prime equals to minus 7x plus lambda. We divide by 2 and we get minus 7 over 2x plus 1/2 lambda. Then we integrate this, and then we get minus 7 over 4 x squared plus 1/2 lambda x plus k1. Then we again integrate. So we integrate this first time. All right, we integrate this function first time to get y prime. Now we integrate it a second time to get y, and that gives us minus 7 over 12 because of that 3. 3 times 4 is 12, plus lambda over 4 because of that x and the 2, and plus k1x plus k2. Now from the initial condition, from the initial conditions up here, x naught equals 0 means that y x naught is 1. Well, the fact that x naught is equal to 0 means that k2 is equal to 0. And from the terminal condition, we get that 5. So 5 is equal to, where does the 5 come from? It comes from here. So we end up with 5 is equal to minus 7 over 12 plus lambda over 4 plus k1. Solving for k1, we get k1 equals 67 over 12 minus lambda over 4. We also have this constraint that the area underneath the y function has to be equal to 10. So now we integrate this y function, which is now what we've calculated. All right, x2 or k2 is 0, so we have left this part of the function, and we're going to integrate that from x0 to x1. So we're going to take that function and set it equal to 10. So doing so, we get 7 minus 7 over 48 times x to the fourth, evaluated from 0 to 1, because x0 or x goes from 0 to 1, x0 to x1. All right, that's where that comes from. And we do the same thing, plus lambda over 4, but we're now cubing that because we've integrated it, lambda over 12, x cubed from 0 to 1, and we have x1, x squared over 2. When we integrate k1, x, we get x squared over 2, and we evaluate that at 0 and 1, and we set the whole thing equal to 10. So now, doing so, we get minus 7 over 48, because we get x to the fourth, 1 to the fourth is 1, minus 0, and that leaves us with a 1. The same thing, lambda over 12, because this will be 1, plus k1 over 2, and we set that equal to 10. And now we can solve this minus 7 plus 4 lambda plus 24k1 is equal to 480. So we take that 480, that 48, and we multiply that through on both sides, which gives us that 4 here, and the 24 times 2 is 48, times k1. And then we can solve, because we know what k1 is, and k1 is 67 over 12 plus lambda over 4, and that comes from this here. That's where k1 is, and we set that equal to 487. All right, because we brought that minus 7 over to the other side. And now all we do is we solve for lambda. We get 10 lambda is 353, so lambda is 35.3. So then k1 is equal to 67 over 12 minus 35.3 over 4, and that turns out to be minus 3.2417. So finally we can fill in the y, and we get minus 7 over 12 x cubed plus 8.825 x squared minus 3.2417 x. Now we're going to switch gears a little bit from calculus of variations in a moment to, or in the next lecture, to optimal control theory. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.